Hi everyone. In this video, we are going to do the present value of an annuity. First of all, let's understand the concept of present value of an annuity. In the last video, we did the future value of annuity, right? And the present value annuity basically means how much that future value is worth today. First of all, let's look at the formula. The first one is the description in English. So the meaning of each part in the formula, and this is the formula itself. So make sure you differentiate between present value of annuity and the future value of annuity formula. They look similar, but definitely they're different. For example, this exponent is -1 for future for the current present value of annuity. We have 1 minus in the front. In the future value of annuity, this exponent is positive. We don't have 1 minus. Instead, we have -1 at the end. But anyway, you need to differentiate between these two formulas. The variables in the formula are the same variables you see in the future value of annuity. D represents regular withdrawal. That means periodic withdrawal or your monthly payment for mortgage. R is annual interest rate. K is how many times your account is compounded per year. And is the time in year. So they're all the same. May have in your homework. Basically, we can use this formula to solve two types of account. And the present value of annuity so that people have a better understanding of exactly the meaning of present value. Okay, let's look at it this way. Say this is like a timeline. Let's look at the future value first. This is the now. This is your annuity maturity date. That's future, right? So when you have a future value of annuity account, you keep depositing into it periodically, right? This is each period, you deposit. After so many years, you have a certain amount of money in your account, right? In other words, over the time, your total account value going to increase, right? Going to increase. Suppose this is the total account value. Now this is the one you retire. So when you actually retire, you're going to withdraw money, right? So each time you withdraw money, start from here, you already have a certain amount of money in it. When you withdraw money, each time you withdraw, your total account value will get smaller a little bit. The rest of money still earn you interest, right? Because they are still sitting in your account. Next time you withdraw another amount, the same amount, your total account value going to reduce another little bit. The rest of money still earn you interest and keep going. In other words, when you start withdraw money periodically, your total account value is like unwind from this one, kind of smaller until you get zero. And that's what's happening in when you withdraw periodically. If you remember the characteristic of an annuity account from the beginning of the last video, whenever you deposit or withdraw periodically with same amount, that is annuity. The difference between the present value of annuity and the future value of annuity is that in the present value of annuity, you don't have money to begin with. You start depositing money into it periodically so that your total account value getting bigger and bigger and bigger, right? But when you withdraw money, you have to have money in the account in the first place. Otherwise, how can you withdraw periodically, right? In other words, for any present value problem, you have to start with a certain amount of money. whatever that is. That could be the beginning balance in your account, then you start withdraw. That could be the total amount you just deposit into it, and then you withdraw smaller amount periodically. And in either case, that's present value problem. In other words, to identify whether you have present value of annuity, first it has to be annuity, right? That means you do periodic withdrawal. Secondly, you have to have a beginning amount before you can withdraw. That beginning amount is called present value of annuity, because once you started, that's the current value. It's going to get smaller over time. That's present value, present current, right? Beginning value. Okay. This is the first type of question you could have. Find the total lump sum needed in the account. That means in the beginning, so that you can make periodic withdrawal. Second type of question is that you can use this present value of annuity formula to calculate your mortgage monthly payment. The question is why we can use present value of annuity formula to calculate mortgage monthly payment. Now, think about that. To pay mortgage, first you borrow money, right? So this is your total debt to begin with. Each time you make a monthly payment, your total debt going to be reduced a little bit, right? Next month, you make another payment, it will be further reduced a little bit. So over the time, it will dwindle to zero, right? So for example, let's compare you withdraw money from your retirement account, and let's say you have, say, 150K in your retirement account. Each time you withdraw $500 every month, okay? Versus you have 150K debt to begin with because you borrowed 150K. Then your monthly payment is $500 per month. Think about these two situations per month. Is there any difference between these two scenarios? One is that you have 150K in your retirement account, you withdraw $500 per month for yourself and spend it on your family members maybe, versus you have 150K debt, and each time you pay, make a monthly payment of $500 to make it a little bit reduced. What's the difference between these two? There's no difference, 100% the same. Only difference is the purpose. You have same amount to begin with. You withdraw same amount in every month, same period. Only difference is the purpose. This one you spend it on yourself or on your family. This one you pay somebody else. But in terms of mathematics, in terms of account, no difference. Each account starts with the same value. Each month reduced by the same amount at the same term for the same term. What's the difference? No difference. That's why, mathematically speaking, present value formula and mortgage payment formula are the same thing. They are exact same thing. Okay, now let's look at our first example. Example 1, find the lump sum amount that could be deposited in a bank account today at 8% compounded quarterly to allow 4,000 withdrawals. 4,000 withdrawals at the end of each quarter for, why there's no numbers here? For, let's say, let's just make up a number. For how many years? It really doesn't matter. Let's make it 15 years. Now, round your final answer to the nearest cent. Now, first of all, always try to identify what kind of problem we have. First, this repeating withdrawal. For your homework purpose, just because you do repeating withdrawal, you also have present value of annuity problem because the amount is the same. You do it periodically, that's making an annuity. And since you withdraw, you have to have certain amount in your account to begin with, right? They ask us how much could be deposited, no matter it's the current balance you already have or the amount you deposit, that's something in your account right now so that you can withdraw periodically. So we are looking for current value of your account so that you can withdraw periodically. That is the present value of annuity problem. So I'm going to write down the formula here. Present value of annuity equals D times 1 minus parentheses 1 plus r over k to the power of negative nk and r over k. I just copy the formula from the first page. This is exactly the same present value of annuity formula. So in this case, we are looking for this one, present value. This is the periodic withdrawal amount, which is 4,000 in this case. So we just plug in numbers. Present value equals 4,000 times and 1 minus parentheses 1 plus, we get 8%. Since we do it quarterly, k equal to 4, and negative nk, n is time in years, 15 times 4, and close parentheses over 8% over 4. So let's see what we get here, and reduce it a little bit. 4,000 times 1 minus 1 plus 0.08 over 4 to the power of negative 60 over 0.08 over 4. Make sure your calculation is right. For this present value of annuity formula, this part inside the brackets is always a positive number smaller than 1, always. This is the nature of this calculation because its negative power really means a reciprocal of this number. And this number is a little bit bigger than 1. Something bigger than 1 reciprocal is always smaller than 1, but it's positive. Negative sign itself means reciprocal, doesn't mean negative number. So just remember this part, this whole thing inside the brackets has to be a positive number below 1. So let's do that. 1, let's clear that. 1 minus parentheses 1 plus 0.08 over 4 to the power of negative 60. Make sure you can tell the difference between negative sign and the minus. So for my calculator, this is a negative sign and this is a minus. They are totally different things. Okay, don't just because they look the same and use them the same way. So negative 60 equals, say, a positive number smaller than 1. And divided by this part on the bottom, parentheses 0.08 over 4 equals, and this number going to be multiplied by 4,000. So multiply by 4,000. See, I don't write anything in the middle to avoid rounding error. So that's what we have. 139,043.55. So what this mean? This whole thing means that, let me zoom out a little bit. This whole thing means that if you deposit or if you have $139,043 today, you will be able to withdraw $4,000 every quarter for the next 15 years. Under the current terms, 8% compounded quarterly. That also means at the end of 15 years, this term, your account value is very close to zero. It's very close to zero. So that's minimum amount needed to sustain this 4,000 quarterly withdrawal for the next 15 years. Okay, let's move on to the next one. We have another example here. And Greta wants to retire in 13 years. At that time, she wants to be able to withdraw 12,500 at the end of each 6 months for 7 years. Assume that money can be deposited 8% per year, compounded semi-annually. They just give us the terms. What exact amount will Greta needed in 13 years? Now, I use this example because there's a common mistake in doing this kind of problems. And the common mistake is that sometimes people use the wrong time for that n in the formula. in this case, we have 13 years, we have 7 years. Which one should we use? Now, let's understand that part first by understanding this information in the problem. Don't just jump to the calculator and or plug a number into formula. And that's never a good way to learn mathematics. We really want to understand the information. So now let's look at it. This is now. This is 13 years later. Here's 13 years in the middle. This is after 13 years, Greta retires, right? Look like about retirement. Let's just call it retires. Retires here at this point. Then as soon as she retires, she starts withdraw this money at this point, 12,500 per half year, every 6 months, right? She will do that for 7 years. That means this part is 7 years. That's what's going on. And what this means is that since this asks us how much money exact amount that she needed in 13 years at this point, how much she should have in her account at this point, so that she will be able to withdraw 12,500 every half year for the next 7 years. Remember, annuity means repeating withdrawal or repeating deposit. This is repeating withdrawal. But this repeating withdrawal of 12,500 only happens for these 7 years. It never happened in these 13 years. That means for your annuity formula, your n, the time is 7, it's not 13, because 7 is part of repeating activity. It's that time. So that's why we need to explain this to understand that. And since we are looking for the beginning value of this withdrawal activity, this is the present value for this activity down the road for the future, present value of annuity. So we're looking for how much she needs to have. That's a present value. Even though relative to now is future, but for annuity, it's present. It's beginning value. So present value of annuity. So that's why we know which formula to use. So we're looking for a present value of annuity again, equals withdrawal amount 4,000. Is that 4,000? No, this time is 12,000. This is for last one. 12,500. And 1 minus 1 plus 8%, compounded every half year. That means k equals 2. And she has 7 years of time, negative 7 times 2. Over 8% over 2. So simplify it a little bit, 12,500. Once we understand scenario, calculation itself is not a hard one. This is some basic calculations. 1 minus 1 plus 0.08 over 2 to the negative power of 14. Yeah. And over 0.08 over 2. So let's use the calculator. 1 minus parentheses 1 plus 0.08 over 2 to the power of negative 14 equals, a positive number smaller than 1 divided by parentheses 0.08 over 2 equals, then we just multiply 12,500. So times 12,500 equals, so we get $132,039.04. That means from now, Greta has 13 years to make her effort to accumulate at least $132,039 so that she will be able to withdraw 12,500 every half year for the 7 years thereafter. This is minimum amount needed. That just give Greta a goal, a motive to make effort to have at least this amount. Okay, next one. So after this one, we're going to look at the mortgage problem. Find the lump sum amount that could be deposited in the bank today, compounded 5% compounded semi-annually to allow this amount of withdrawal at the end of each 6 months for 10 years. Again, repeating withdrawal, we're looking for the beginning amount in the account. That's the exact same situation, just different terms. So let's do that. Present value equals withdrawal amount is 1875. 1 minus 1 plus, and we get 5% compounded semi-annually, k equals 2. We do that for 10 years, so negative 10 times 2. And 5% over 2. Can you rewrite that? Present value equals 1875 times 1 minus 1 plus 0.05 over 2 to the negative 20, and 0.05 over 2. Let's do the calculation. 1 minus parentheses 1 plus 0.05 over 2 to the power of negative 20. Yeah, everything is right. Then divide by parentheses 0.05 over 2 equals, and this number times the withdrawal amount 1875 times 1875. So this number is 29,229 and 68 cents. So if this person have this amount at the beginning of the in the account, or deposit this amount, and the person will be able to withdraw 1875 at the end of every half year for the next 10 years under this terms, 5% compounded semi-annually. Okay, now mortgage example. We have one example, one exercise problem. So we do both as examples. Now, mortgage monthly payment, what's the monthly withdrawal from a retirement account? What's the difference? Only difference in purpose. We mentioned that the formula doesn't really care if you spend that $500 per month on your own, or you pay somebody else. It just take $500 away from that total account value every month. So mathematically, no difference. That's why we can use present value of annuity formula to solve mortgage problems. So let's look at this particular one. You want to take out a 140K mortgage. The interest rate on the loan is 6%, and the loan is for 30 years. How much will your monthly payment be? So as soon as you say monthly payment, that's repeating, right? Same amount, right? That's annuity. Since you start with a certain value at the beginning, that's total debt. You start from this one, you reduce it, right? That's the present value. Present value of annuity. That's the formula. But only thing different is that this time we're looking for this monthly payment, periodic withdrawal, right? Withdrawal means reduce your total amount. No matter that amount is your retirement account, your money, or the amount that is your total debt. It's just a monthly amount to reduce. Okay, future value, this is present value. In this case, is 140K. Make sure you put it on the left-hand side because that's your present value you want to reduce when you withdraw. And we are solving for D. 1 minus parentheses, 1 plus interest rate is 6% monthly. That means 12 negative. This is 30 years times 12. And we have 6% over 12. Let's reduce it a little bit. Let's reduce it a little bit. So 140K. 140K equals D times 1 minus 1 plus 0.06 over 12 to the power of negative 360 over 0.06 over 12. So we're going to calculate this whole thing on the right-hand side and write it down as a single number, and then later on we divide that number on both sides to get D. So that's our strategy. So let's calculate this number. 1 minus parentheses 1 plus 0.06 over 12 to the power of negative 360 equals divided by parentheses 0.06 over 12 equals. So we get this number 166.79161144. So everybody can do simple division, right? We're going to use 140K divided by this number. Divided by this number. Let me tell you before we do the division. Time is money. I mentioned this several times. So if you have longer time and your monthly payment is going to be low, that's the information. But that doesn't mean your total payment out of pocket money is low. Actually, it's highest among different terms. 30 years is worst among 30-year and 20-year, 15-year mortgage in terms of how much you pay in the end. So divided by 166.7916144. So we get, let's write it here. D equals $839.37. So that's the monthly payment. So as long as you can identify you have a mortgage payment problem and you use the present value of your annuity formula. So this is the last one for this video. Janine, I guess is how to pronounce it, but I'm not 100% sure about that. So just call it Janine. Janine bought $3,000 of new furniture on credit. That means she borrowed the whole thing, $3,000. That's the total debt. Because her credit score isn't very good, the store is charging her a fairly high interest rate on the loan, 16%. 16% is not fairly high, it's very high. It's like robbery, basically, in my opinion. If she agreed to pay off the furniture over 2 years, how much she will have to pay each month? Say, current debt, and we're looking for monthly payment. So current debt is the current value of annuity because she make a periodic payment, then we periodically same amount reduce our total debt. So 3,000 equals D times 1 minus 1 plus 16% monthly payment 12 and 2 years negative 2 times 12. Don't forget negative sign is the present value formula. 16% over 12. Now rewrite it. 3,000 equals D times 1 minus 1 plus 0.16 over 12 to the power of negative 24, 0.16 over 12. So let's calculate this to see what we get. One minus parentheses 1 plus 0.16 over 12 to the power of negative 24. Yeah. Then divided by parentheses 0.16 over 12 equals, yeah, we get a 20.42353,906. So we are going to use 3,000 divided by that number. So let's do that. 3,000 divided by 20.42353,906 equals. So we got 146.89 cents. So this is the monthly payment. And that's the end of this video. Bye, everyone.